Hello, my name is Armin Sadri, and I'll be presenting a paper titled Equalization Techniques for Reducing Intersymbol Interference in Wireless Digital Communications for EEE6509 for the spring 2016 semester. Over 4 billion individuals use wireless digital communication every day through digital cellular networks. A problem shared by all channels used for digital communication is intersymbol interference, or ISI, caused by attenuation distortion, which, if left unaddressed, can introduce errors in received signals. Equalization is one method that can be used to reduce ISI by filtering incoming symbols with a variety of algorithms, including MMSE, blind, Viterbi, and BCJR equalizers. This project seeks to survey existing digital equalization techniques applicable to wireless communication to explore the richness of channel interference mitigation, and provides a small comparison MATLAB simulation of an MMSE and zero forcing equalizer. The outline for this presentation is as follows. I will begin with an introduction that will explain the problem of ISI and the solution in equalization. I will then explore 4 equalization methods, including MMSE, blind, Viterbi, and BCJR. I will then present a small simulation of example code that I ran in MATLAB, and I will finally end with a conclusion. Intersymbol interference, or ISI, is an unfortunate element of almost any channel used for digital communication. ISI can be primarily described as a result of a receiver receiving multiple echoes of a transmitted symbol. The signal received in a hypothetical channel is a convolution of the transmitted signal and the impulse response of the channel, as well as the addition of noise, as represented in equation 1. Convolution in this case is indicative of a form of channel memory. With this in mind, the received signal can also be represented by a weighted sum of each echo signal multiplied by the channel's impulse response, with the addition of thermal noise, as represented in equation 2. Viewed in this way, the ideal received signal would be the time index 0 term for both channel impulse response and transmitted signal. Unfortunately, what is actually received is the time index 0 term, as well as a sum of time index terms corresponding to the echoes of the transmitted signal multiplied by the channel's impulse response at that time index. The function of an equalizer, then, with the complications and issues surrounding ISI in mind, is to filter the received signal to eliminate the sum impulse responses and transmitted signals corresponding to time indexes other than time index 0, such that the received signal approximates the ideal received signal, specifically a received signal term with added noise. The first equalization technique to be explored in detail is the MMSE equalization technique. The MMSE estimator equalizer seeks to rectify the blind application of channel impulse response terms as seen in the zero forcing equalizer by treating the received signal in terms of Bayesian probability. The basic idea of the MMSE estimator equalizer is to balance the effort spent to minimize ISI and noise, such that the SNR is maximized. The SNR in this case is defined as the expectation of the received signal power divided by the expectation of the received noise power, represented in equation 4. The received noise power is the received signal subtracted by the MMSE filter convoluted with the noise and channel response. The solution to this estimation problem is a match filter acting on the complex conjugate of the channel impulse response convoluted with the added noise. In its normal implementation, the MMSE estimator equalizer acts as a zero forcing linear equalizer in the presence of low noise. In the case of high noise, such that the ISI noise is lower than the channel noise, the MMSE simply amplifies the signal and ignores the ISI contribution to noise and acts as a matched filter. The MMSE filter implemented in 1 utilizes turbo equalization that, instead of relying on a maximum a priori or MAP equalizer to make decisions based on the de-interleaved a priori information, utilizes a linear filter with parameters that are constantly determined by an MMSE schema. Turbo equalization utilizes the known interleaving schema in order to provide a secondary source of information regarding the original bit stream, secondary to the channel impulse response information which dictates the intersymbol interference. This information takes the form of a priori probabilities, which can be used with Bayes' theorem to provide probabilistic determination of the original bit stream. The method used in 1 trades the computationally complex but optimal map decision equalizer following the turbo equalizer coding with a linear equalizer that changes parameters with a minimum mean square error algorithm updated per symbol. Equation 5 represents the equation for the linear estimator used by 1, and equation 6 shows the cost function for the MMSE solution. The results from 1 are reproduced here in figure 1, showing that the MMSE equalization method approached the map before 5 iterations. The MMSE implementation from 2 means to optimize performance in an orthogonal frequency division multiplexing, or OFDM, system with a linear MMSE filter. The MMSE equalizer in 2 takes advantage of the multiple narrowband signals inherent to OFDM systems in order to apply Bayesian decision-making on each channel simultaneously. a marked difference from what the authors partition as serial MMSE equalizers. The optimization gained from using the linear MMSE equalizer in 2 is enhanced by selectively choosing subcarrier channels in the orthogonal frequency division multiplexing system which do not possess significant signal energy. These carrier channels are termed in 2 as virtual subcarriers. The model for the orthogonal frequency division multiplexing system used by 2 represents a marked similarity to the equation for the signal received in a hypothetical channel represented in equation 1, and only differs in its modeling of the frequency division multiplexed subcarrier channels with vectors as represented in 7. The subsequent block MMSE equalizer in 2, derived from the solution to the noise estimation and minimizing problem, is presented in 8 and closely resembles the cost function for the MMSE solution presented in 6, for the related minimum mean square equalizer from 1. The results from 2 are produced here in figure 2, showing that the linear block MMSE equalizer method approached the serial MMSE equalizer. The second equalization technique to be explored is the blind equalization technique. The blind equalization technique eschews the need to analyze the symbols themselves, as in MMSE equalization, by building statistical information directly from the transmitted signals. The blind equalizer discussed in 3 is based on the following model of the received baseband signal represented in equations 9 and 10. Equation 9 bears a striking resemblance to equation 2, but is built with a constellation information signal term instead of an explicit received signal term to signify the non-reliance on symbols for estimation of h. In 3, they developed their blind equalizer through a simulation of a 16-QAM signal, with the resulting process outlined in figure 3. The BER versus SNR for the blind equalizer in 3 is reproduced in figure 4. An additional estimation of blind equalization was explored in 4, which focused on the constant modulus criterion, or CMA. The CMA criterion blind equalization attempts to return a received and equalized signal to the pre-channel or otherwise specified modulus, as transmission through a noisy channel with ISI can deteriorate the modulus of the transmitted signal in a predictable format. The cost function central to the CMA criterion blind equalization technique is represented in equation 11, and the term to be minimized is the JCM term. The conclusion of 4 indicated that under ideal conditions, the performance of the CMA criterion blind equalizer approached that of an MSE cost function as depicted in figure 5 from 4, which shows the contour surface plot of both cost functions. The Viterbi equalizer utilizes the maximum likelihood estimation method to calculate the received signal. By converting the received signal into a binary string, a trellis diagram can be composed of the states of the receiver over blocks of time. The received signal levels can be used to create a maximum likelihood path through the trellis diagram, or, in other words, given the bit sequence, the path of the maximum likelihood of having occurred. The Viterbi algorithm builds a set of likelihoods for passage through the trellis and chooses the path of the highest set of likelihoods. In 5, the Viterbi equalizer is composed of 2 Viterbi algorithm blocks, a soft decision Viterbi algorithm block and a maximum likelihood block. The function of the soft decision block from 5 is captured by equation 12, which shows how the likelihoods from the second block are calculated as the probability that the first stage's estimation was incorrect, given the receiver's input. The second block utilizes the likelihood metric given in equation 13 from 5, taking into account the trellis path, tap gain, and the instantaneous SNR. The equalizer was simulated in a multipath channel for an assumed GSM modulation scheme, and the output is reproduced in figure 6. In contrast to the Viterbi equalization algorithm, the BCJR equalization algorithm seeks to maximize the a posteriori probability. This translates to minimizing the bit error rate directly, as opposed to the Viterbi treatment of creating the most likely bit stream, which is akin to minimizing the differences between the received and transmitted symbol stream. Similar to the Viterbi equalization algorithm, the BCJR algorithm functions on a trellis, which presents bit interactions for each time slice. The a posteriori probabilities arise in the forward and backward recursions for the trellis. Because the BCJR algorithm involves significant computational expenditure, much of current research is aimed at reducing the complexity of the algorithm used. The standard BCJR algorithm recursions are given by equations 14 and equations 15 from 6. The alpha and beta terms have the following probability equivalencies seen in equations 16 and 17 from 6. The final probability equation for the BCJR algorithm is given in 8 as equation 18. The proposed algorithm in 6 for reducing the complexity of the BCJR algorithm begins with a modified MBCJR algorithm, which simply divides equation 18 by equation 19 and optimizes the result by segregating the ISI channel into 3 cases: a minimum phase, maximum phase, and mixed phase section. Each case is treated differently by the algorithm, according to which portion of the BCJR algorithm performs the best. The results of 6 are replicated in Figure 7 for mixed phase channels and in Figure 8 for the minimum and maximum phase channels. The simulated results were compared with MBCJR and RSBCJR algorithms and showed slower BER increase with EBNO increase, but achieved 64 times lower complexity. The second paper reviewed for the BCJR algorithm utilized the TBCJR scheme, which is similar to the MBCJR method in that it reduces the required backward recursion trace when the trellis path falls below a certain threshold. The results from 7 are reproduced in Figure 9. As an additional exercise, a MATLAB simulation comparing the performance of an MMSE equalizer and zero-forcing linear equalizer with BPSK modulation in a channel with simulated intersymbol interference was performed from the code developed in 8. The simulation first created a simulated BPSK transmission by randomly generating a binary sequence with 50% probability for either a 0 or 1, and then simulating modulation. The multipath channel impulse response was modeled with 3 delay taps and included a white Gaussian noise generator in order to simulate channel noise other than ISI. The simulator then performed both zero-forcing and MMSE equalization on the simulated transmitted signal, and then counted the bits that were in error. The resulting bit error rate was used to create Figure 10, generated in MATLAB from the code in 8. The author of 8 noted that there was a 0.5 dB difference between the 2 equalization methods, with the MMSE equalizer outperforming the zero-forcing equalizer. In conclusion, equalization is a powerful tool in mitigating the effects of intersymbol interference channel distortion. 4 equalization techniques were briefly explored in this research topic, including MMSE, blind, Viterbi, and BCJR equalizations, as well as several modifications to these equalizers that sought to reduce complexity or reduce error. From this study of equalizers, the only unambiguous conclusion can be that there is no one perfect equalizer for every situation. Modulation encodings and channel environments can drastically affect the efficacy of an equalizer. An important takeaway from this project would be that each of the equalizers presented could be treated individually for subjects of research with even greater depth than this paper, which only approached the various equalizers at the very surface of the breadth of knowledge available. The MATLAB simulation was also very insightful into the actual effects of intersymbol interference on a received transmission, as well as the algorithmic process of equalization. The process of researching this topic was also very rewarding, as many papers were consulted and evaluated in novel ways for this researcher. Thank you for listening to my presentation. Goodbye.